Okay. So today we're going to very much switch gears and talk about a particular computation the brain does, decision making. And decision making under a particular kind of decision making under time constraints. And I'll be very clear and shortly what that means. Okay. So let me give you a little background. So historically in neuroscience, the focus has been on sensory processing and motor control. And the reason for that is both of those are kind of near the periphery. So here's your brain. And we have sensory input. And that comes in here, let's say sensory input. And then we have, on the other side, we have motor output. Which also comes from some small region of your brain, or actually a relatively large region. And inside is all the thinking. That goes on. Okay. And the thinking in some sense is what we really care about. But it's much easier to study sensory processing. You can show images and record from neurons. You can ask an animal to do something and record from neurons in, say, visual cortex, record from neurons in motor cortex. And there's a fairly short link between sensory input and what's happening in visual cortex and what's happening in motor cortex and then output of your muscles. So neuroscience knew about this, but this was just easier to study. But of course, this is what we care about. And to get a handle on that, people have been thinking about this for a while, but around, let's say, 1990s, people started studying decision making. Studying decision making. And decision making, so involving integrating evidence over time. Okay. And could give you an example of the kind of problems they're considering. I'm going to give you guys a task. And let's say we have 2 coins. Hold on. Okay, 2 coins. Coin 1, number 1, probability of heads. Equals 0.6. Okay, it's not a fair coin. 60% chance probability of heads. Coin number 2. probability of heads equals 0.4. Okay. Okay, let's say I pull one of these coins from my pocket and start flipping it. So it got heads, tails, tails, heads, heads, tails, heads, so on. Okay. And we're gonna play a game. And the game is, so you guess which coin it is. Okay. If you guess right, you get 100 on, probably pronounced wrong. Okay. If you guess wrong, you lose 100. Oops. I'll make it too horrible. You lose 100. YUAN. Lose 100 yen. Okay. And the question is, so this is kind of an easy game. If you you can, and so there are sort of, the strategy you have to have, the strategy, you kind of count heads and tails, and is really about when to decide. Okay. And the trade-offs are obvious. You could wait for, so the trade-offs are, there's a speed accuracy trade-off. Okay. So if you guess quickly, if you take a long time, if you wait until you're sure, you'll get high reward per trial, right? Every time if you wait for the 1,000 coin flips, and they're more few, if they're around 600 heads, you'll guess coin one. If they're around 400 heads, you'll guess coin two. You're going to be right just about every time. On the other hand, average reward per unit time is small, right? If you do that, you get basically 100 yuan for every 1,000 coin flips, which is 0.1 yuan per coin flips, which is not so much. You can take the opposite strategy, which is basically guess on the first coin. And you'll be right, actually, more than half the time, and that you'll get it. And you can actually work out how much you'll get. Okay. So this is a really common, the speed accuracy trade-off is really common in this kind of decision making. You think of all sorts of examples. It just happens in just about everything you do. You have to decide when to decide. Okay, and you have to spend, how much time do you spend studying for things? So studying for a test. Okay, ordering in a restaurant. Even dating. Oops. They're dating. When do you get married or break up? Looking for an apartment. Okay, so all these involve a speed accuracy trade-off. Okay, and in this game, what I may not have told you is you get to play this game over and over and over again, as many times as you want. And in this case, so in these cases, you know, you're not necessarily going to do these things as many times as you want. You study for tests very often. You order this all the time. You may date more than once. Looking for an apartment. It doesn't happen very often, but the more time you spend on it, the higher your accuracy. And the speed is important because if you're not doing this task, you're going to be doing something else. All right. So the reason you don't study for a test, you know, for every single waking hour for a week is because you have other things to do. Right. Time is valuable. And we'll actually see that explicitly later on. Okay. So what I'm going to talk about today, I'm going to talk about first the standard approach to this problem. Oops. Approach. It's called drift diffusion models. And these models were kind of made up because they seem reasonable, and as we'll see, under some circumstances, they're optimal. So I'll say a few words about that. Then I'm going to talk about the actual brain. Okay, because it's known where in the brain some of these computations are taking place, or at least we thought we knew. Turns out we know less than we thought, but we can sort of see, we can see aspects of these drift diffusion models in the brain. And then finally, I'm going to put so theory. So we're going to sort of solid mathematical foundation. And then more on the actual brain. Okay, so it's going to be a mix of theoretical analysis of this problem, and then also little neuroscience, what goes on in the brain. Okay, so let's start with drift diffusion models. So if you go back to this problem, oops, wrong problem, wrong page. So this is just a math problem, right? You know everything about it. And you should be able to find an optimal policy, an optimal mapping from number of coins to a guess that's going to maximize your reward per unit time. And it clearly depends on the payoffs, right? If it's 100 yuan for getting correct and 0 for getting wrong, the best thing to do is just guess. In fact, you just, one coin flip, just guess. You don't even have to guess. You don't have to pay attention, right? You'll get, average of if you guess completely randomly, 50 yuan per coin flip, a little higher if you guess, if you look at the coin. On the other hand, if you're wrong, you lose 1,000 yuan, you'll wait a long time, okay? And there are cases where you'll simply just, whatever. Okay, so let's talk about drift diffusion models. So one sort of, without thinking too hard, here's how we might play our game, our heads tails game, okay? So we just, on this axis, oops, we just, This is number of flips. And we plot heads minus tails. Number of heads, NH minus NT. So this is number of heads. And this is number of tails. Okay. And so what's going to happen, right? We, start here. This is time one. So it's going to be plus or minus. It's either going to go, well, down, might go down again, might go up, might go down, it might go up, down, up, down, up. Oops. Oh, man, that should not have done that. Okay. Okay. So we start here. It's one, and the next one we go down. Next one we go up. Different sequence than last time. Down, down, up. Finally, it goes up. And what we do in our policy is basically just set some bounds. And I think I'd be better at this by now. It's just set some bounds. And if we hit this bounds, we say it's, so we hit the bound here, we say it's coin number one. And if we hit the bound down here, we say it's coin number two. Okay. And so you can sort of build a model like this for any distribution. It doesn't have to be coin flips. For instance, I'll give you another example, which I'm going to talk about later on. It's called the random dot kinematogram. Kinematogram, possibly spelled wrong. And this is an experiment I'll be talking about. So a subject, sometimes a monkey, sometimes a human, views a screen with moving dots. Okay, and each dot moves in a different direction. This dot might be going that way, this one going that way, that one going that way. They're kind of randomly distributed around the screen. And the coherence equals C equals fraction of dots. Dots moving right. To the right. And the job of the subject is to look at this and decide whether they're moving right or left. If they move right, they get, if they're monkeys, a juice reward. If they're humans, they get cash. If they guess wrong, they get nothing. Or sometimes they get a timeout. They have to wait extra time until it appears on the screen again. But now instead of a coin flip, we can think of xt, x time t equals noisy evidence the dots are moving right, moving right. And that will equal C plus the true contrast plus noise, squiggle T. So this is noise. And if we take it to be Gaussian, it doesn't really matter. So again, we have the same setup. We start here, and we can actually, on this axis, we put the sum on T of xt. Okay. And this, of course, let's say, let's actually do the sum tau equals 1 to t of xt. And this, of course, equals c times t. That's a drift rate plus the sum tau equals 1 to t of squiggle t. So this term is drift, and this term is noise. Oops. This term is noise. And the reason it's called diffusion is, so if C were positive, the drift term would give us something like this, but what we'd actually observe, of course, was fluctuations around here, which actually just get bigger and bigger. And again, we can put bounds here and here. And when we hit one of these bounds, so dots are moving right. And if we hit this bound, we say dots moving left. Okay. And then the whole problem is to set the bounds. Okay. And we want to set the bounds to maximize the reward phenotype. So the point, I mean, we're going to come back to the random dot kinematogram, which is why I introduced it. But the point is you can use any kind of noise at all. And later on, we'll even use noise and spikes, which are noisy things. So in this case, oops. In this case, the noise was this sort of Bernoulli noise from coin flips, which are random. And in this case, the noise was from Gaussian noise because basically the number of, if you have a bunch of errors on it, the number of dots actually moving to the right at any one time is going to fluctuate. So in this case, I didn't tell you dots appear and reappear randomly. Okay, so the first question we want to ask is setting a bound a good idea? And for that, what we can do is, what do we want to know? Okay, what we want to know, let's back to the coin problem. So back to the coin problem. What we want to know the probability that it's coin one given data. And the data is head-tail sequence. Well, sequence of coin flips. And since there are only 2 coins, we can actually take the ratio. Turns out to be easier quantity to work with than. Okay. But this, of course, only works if you had 2 coins. If you had 3 coins, that wouldn't work at all. Okay. So what is this? This is probability from Bayes' theorem. This is probability of data given coin 1 times the probability of coin 1. This is a prior over P of data. Times, that's the numerator. The numerator is this. Denominator, this just flips over. P of data given coin 2. P of coin 2 divided by, well, P of data. And and the reason we actually look at the ratio is because the P of data is cancel. And we just get equals, I'm going to put the P of coin 1 first, P of coin 1 over P of coin 2. This is the prior times P of data given coin 1 over P of data given coin 2. P of data given coin 2. So we're doing nothing but base there, okay? So all we have to do is write down what this is. So let's be more explicit about our coins. We have coin 1. We're going to write P of heads to be general equals P1, it's just some number. In the previous case, it was 0.6, but now it can be anything. In coin 2, P of heads equals P2. Previously it was 0.6, and previously it was 0.4. Okay, but these could be anything. They just have to be different, right? And so let's say a sequence. So P of data given coin 1 equals, the data is something, like heads, tails, tails, heads, heads, tails, given coin 1. So basically this is equal to, every time you get a head, this is P1, and each tail brings down a 1 minus P1. Probability of heads is P1, the probability of tails is 1 minus P1, ... So this is basically equal to this. And this is just a counting process. For every head, we get a P1. For every tail, we get a 1 minus P1. So this equals P1 to the NH. Oops. P1 to the NH times 1 minus P1 to the NT. So NH equals number of heads and NT equals number of tails. Okay. And so for P of data given coin 2, equals P2 to the NH, 1 minus P2 to the NT. Okay. And now if you go back, what we want, remember, is the ratio of these things times the prior. So let's go, so we can write it here. P of coin 1 given data divided by P of coin 2 given data equals P of coin 1 over P of coin 2. This is a prior, times P1 to the NH, 1 minus P1 to the number of tails, oops, NT divided by P2 to the NH, 1 minus P2 to the NT. Okay, so there's a rule in probabilities that you should always take logs. Actually, we can write this as this term times P1 over P2 to the NH times 1 minus P1 over 1 minus P2 to the NT. Just 1 second. Sorry, Mindy. Yeah, I forgot to tell you. Next week. Sorry about that. Okay, so we take logs of both sides. And when we do that, we get log of P of coin 1 given data over P of coin 2 given data equals log P of coin 1 over P of coin 2 plus number of heads log P1 over P2 plus number of tails log 1 minus P1 over 1 minus P2. And we'll assume that P1 is greater than P2, which implies that 1 minus P2 is greater than 1 minus P1, right? So we're going to write this term here as NH. Actually, let's leave some more space. So this, we're going to write this NH. So we're going to write this as log P1 over P2 times NH minus log 1 minus P2 over 1 minus P1 times NT. Okay. So this is what we wanted. So this, if we know this quantity, assuming we know the prior, then we know the log of the probability that we're going to guess a coin correctly. It's kind of cool. So really we want some linear combination of NH minus NT. And that's why we could, and so in our initial example, right? So our example, we had P1 equals 0.6, P2 equals 0.4. So P1 over P2 equaled 6 over 4, which is 3 over 2. And 1 minus P2 over 1 minus P1 also equaled 6 3/2, right? So both of these numbers were the same. So a previous example, what we should have put on the axis was log 3/2 times n number of heads minus number of tails. Okay, but that putting this term in doesn't really matter. Just all it does is affect the bounds, affects the bounds. Okay, so that was our previous example. But what we really want to put on this axis, of course, so this is a previous example. Oh. But in general, okay, what we want to put on the axis is log, log P1 over P2 times n number of heads minus log P2 over P1 times number of tails. Okay, and our starting point should be log, so starting point is log P of coin 1 over P of coin 2. And if we do that, we can just, wherever we are on this, we're going to say, we're going to jump up. Going to go up, down, down. drifting along. So no matter where we are, we can read off exactly the probability just from knowing this axis, which is basically this term plus that term, tells exactly the probability that we're going to be correct. Okay. And we get set bounds, and when we set the bounds, we know the probability we're going to be correct. It turns out you can compute all this stuff analytically. You can write down analytic expressions for, well, so you know if you set the bounds here and here, you know exactly the probability, but you can actually compute analytically the time it takes to reach the bounds. And so you can compute analytically reward per unit time and solve the problem. But that's a rare case. Normally you can't do that. Okay, so this idea, so basically this idea of drift diffusion comes from, okay, we're going to compute this quantity, and this quantity depends on, sorry, the quantity, let's be clear about what the quantity is. This is what we care about, probably that we're going to make the correct decision. And that turns out to be a really simple function of the data. We just accumulate, and we count heads, we count tails, we multiply by these constants and put them on this axis, and we just and we integrate, and then basically we put bounds here. This is our coin 1 bound, and our coin 2 bound. And that's the whole story, okay? And so this is really the idea behind these drift diffusion models. As we'll see, took a long time for people to realize this. There's sort of, this works great with 2 coins, but it doesn't work if you have more than 2 coins. And in fact, it doesn't work at all for these drift diffusion models, because the coherence, if the coherence only took on 2 values, flat bounds would be ideal. But because it can take on more than 2 values, we can still use this idea to compute the probability of the dots going to the right or to the left. But it's a little harder to turn that in. It's not all clear the bounds should be flat. And actually we'll see why. Okay, so let me now switch gears a little bit and talk about random dot kinematogram in a little more detail. I already showed you this is a picture you should have in mind. Actually, let me just draw the picture again, so it's totally clear. So we have screen, we have moving dots, moving kind of random directions. And the dots the dots flicker on and off. Okay, so they're not streaming, they flicker on and off. And C equals coherence equals fraction of dots moving to the right. Okay. And if C equals 1, so C equals 1. So C equals 1. I've seen, it's really easy. You just see a bunch of dots streaming to the right. It's really easy. You know pretty much immediately which way they're going. C equals -1. They're also streaming to the left. You see really easily. This is a really easy task. But somewhere around C equals, this is C approximately equals 0.5. It's really hard, and you have to stare at it a long time to get a sense for which way the motion's going. And you can see this in what's called psychometric and chronometric curves. So these are sort of important names in decision making. So they're psychometric curves. Is basically probability of make a right decision versus coherence. So this is coherence on this axis. See, this is -1, 0, 1. This is probability, so 0, 1. This is probability. Oops. Of choosing right. And here is at 0.5, 50, 50. And you see, not surprising according to what you think here. If its coherence is -1, the probability of choosing right is really small. And then they go up like this. Yeah, there's extremes that they tend to work pretty well. It's not really a good picture of what it actually looks like. It kind of looks like. So it depends on the animal. Okay, psychometric curve. There's also, and so that's not so surprising. There's also something called a chronometric curve. Which is the time it takes, size, which is how long it takes to make a decision. Okay, this again is C -1, 0, 1. This is now time. 0. And it tends to, not surprisingly, at intermediate coherence, it goes up and then comes down. So the animal is really fast out here and much slower here. And the reason this isn't 0 is because it just takes some time for information to propagate through the brain and for the animal to move. Okay. And monkeys and humans show very, very similar psychometric curves and chronometric curves. People now do these tasks in all sorts of media. They show clicks in animals' ear, the right ear versus the left ear. They have to indicate whether there are more clicks on the right than the left. They even do this on humans as well as animals. They have other visual stimuli besides random dots. So this is really, really, really common. Okay. And so let me tell you a little bit about the brain areas involved. So you kind of need two things. So if you go back to sort of this coin flip, there's evidence, and then so the evidence is coming in from sensor areas, and then you have to have some area to integrate the evidence. Okay, and we saw earlier this is why you need things like line attractors. Line attractors are very good at integrating evidence, as we saw. So for the random dot kinematogram, you need neurons that detect motion. So neurons in MT, which is medial temporal area, detect motion. So if you plot the firing rate nu of a neuron in MT versus coherence, this is C, this is -1, 1, and again 0. You'll see two main kinds of neurons. So neurons that go like this. So these are rightward preferring neurons. And you also see neurons that go like this. And these are leftward preferring neurons. Oops. Okay. So this is tuning curves. I don't know if you've heard about this. Tuning curves are pretty common in the brain. So sensory neurons are tuned to various things in the environment. These are tuned to speed or velocity. So firing rate here might be 30, pretty high, 30 or 40 hertz if the coherence is positive, and maybe 5 or 10 hertz if the coherence is at -1. So these are the opposite, right? These neurons fire like mad, 30 or 40 hertz when the coherence is at -1, and then relatively slowly when the coherence is at positive. So now we can do just what we did in the coin flips without thinking too hard. So we can plot on this axis so we can look at more than one neuron. There are many neurons, rightward preferring neurons, and many leftward preferring neurons. And so remember that, so one thing that's important to remember is that this neuron, if it's firing, right? So a neuron versus time, what it does is generate spikes, right? So these are the spikes. So, you know, if you can, spikes themselves, they're kind of noisy, right? If you're looking at these spikes, you'll see, oh, here's a neuron, here's a spike. It takes you a while to realize what the firing rate is. So what we can do is plot it as sort of the first class on this side. So number, so this is number from R minus NL. So this is number of spikes from rightward preferring neurons and this is number of spikes from leftward referring neurons. Okay, so you know most of the time it's going to be these are spikes. So we're just counting these spikes, and we're counting as well. We're also counting these spikes, right? These neurons are also spiking. So in this case, they're spiking a little more slowly, and so well, let's make it really slowly. So, but it takes a while to figure out that these neurons are firing at higher rates than those neurons. Okay, so when you plot this, what you're going to see is, you know, no spikes, then you get a spike here, and they're going to come at sort of irregular times, maybe down, up, maybe you get a couple downs, up. And again, we can set bounds, okay? Set bounds. And this is choose right. And this is choose left. And the job of the animal is to decide where to set those bounds. Okay, so what this tells you is you need some neurons that count spikes, okay? And they don't have to count the difference. They could count the number of rightward spikes versus the number of leftward spikes, but they somehow have to subtract. And as we saw earlier, maybe we don't want exactly, you know, the coefficients maybe aren't exactly one for both of these, but it's going to be something like that. So it turns out that neurons like this have been found in the brain. So LIP, so neurons in LIP, which is lateral intraparietal area. Numerically, I know that name. Count spikes. Okay. So basically and experimentally, so I've been talking for a long time now. I'm going to actually take a break, 5-minute break, and come back and tell you what happens experimentally, and then talk a little bit more about theory. Okay, so let's take a 5-minute break now. As usual, I'll be here if you have any questions. Okay, I'm back. So let's see what people found in LIP. So remember MT, MT was a very so this is MT, it's a very simple sensor area. What about LIP? In LIP, they found kind of what you'd expect. So it's a little bit, the story's a little bit more complicated. So here's a picture of LIP. So LIP is an area that's actually has a topographic organization. Which means it's really, it mirrors outside world, mirrors outside world, outside space. Okay. So for instance, if you, and so this basically, oops. So look at, so neurons here, that's how shall I say this? Let me erase this, draw two pictures. So here's, actually, let's try like this. So here's a computer monitor. And if you show sort of an RDK, so moving dots here, what you'll find is if you look in LIP, this LIP, you find neurons over here that are responsive to, they respond to, well, respond to movements. So if you stuck an electrode in here, so what we're going to do, you stick an electrode in, oops, oh man, I think I would learn. So you stick an electrode in here and you record spike trains. And what you find is that for rightward preferring neurons, this is time. So this is time relative to a decision. Okay. And this is firing rate. So at high coherence, what you'll find is things ramp up quickly, and then at a decision rate, they drop off. Okay, so this is decision is made at this time, and that's when these neurons at this high coherence have peaked, and then the thing is, but at different coherence, so lower, this is low coherence. It really actually, let's make this a little more realistic. So basically, once it makes a decision, these fall off very rapidly. Okay, and different coherence, the same thing. It peaks in the same place. Okay, just takes longer. Remember, we've aligned to this. Okay, so this is C, let's say equals 1, and this is C equals 0.6. It takes longer to integrate. And then on decisions where this is let's say 0.6. So this is right decisions. And then if the animal actually made a leftward decision, it would start somewhere and would actually, so this is leftward decision. And actually, this is wrong. It actually goes down a little bit. It's actually, oops, oh man. Okay. And leftward decision, activity actually sort of drops. Okay. So this is kind of nice. This is an area that's really looks like it's integrating information, right? This is exactly what you want. Not only is it integrating information, but it's integrating information to a bound. So it looks like it's doing exactly what theory predicts. Now, there's one problem with this, and that is they inactivated this region. They inactivated this. That's a very common thing to do in neuroscience. So this is really correlational. All right, you see a relation that, you see that the firing rate goes up and then this animal makes a decision, the firing rate drops. And it looks really like this is an area that's making a decision. They inactivated this region it had, which is really common, right? So if you want to make something a causal statement, you want to show that this area is actually necessary for this, no effect on behavior. Okay, none whatsoever. So this was a bit mysterious. We have this area that looks like it's doing exactly the right thing, but it's not affecting behavior. So my grad student actually has a theory. When you make a decision and you're wrong, so we have to give you a little background. So what the animals have to do is the experiment goes like this. So they have to focus first on some point on the screen. So they focus here. Doesn't really matter. They focus at some point. Oops. So they fixate. So they fixate on some point. They fixate. And then the moving random dot camera comes on, they look at it for a while and they move, and they indicate a decision by they moving their eyes. So move eyes. Move eyes to indicate decision. Okay. And so if you move your eyes to indicate decision and you're correct, everything's fine. But if you're wrong, you actually don't know why you're wrong. Either you made the wrong decision or you moved your eyes to the wrong spot, right? Maybe to get a reward, it turns out if you move your eyes over here, so if you move your eyes, for instance, to here, you get no reward. Because you didn't move them to the right spot. All right. So you need something in your brain to keep track of where you move your eyes to, and LIP may be doing that. But the truth of the matter is we have no idea what LIP is actually doing. Okay. The story was really simple here until people did more experiments. Okay, so I'll put the relevant papers online. What I want to do now is switch to understanding in a little more detail, a little more mathematical detail, what we do when we have these complicated situations for coherence. So remember, we had our old picture with only 2 coins. This is called the log odds. We could compute that. And there was just one piece of evidence. We had this one quantity we had to keep track of. In the case of coherence, we can't do that, right? There are actually infinite number of coherences, and the situation gets more complicated. And so I'm going to actually talk a little bit about that, and then I'll go to the treatment of this as a reinforcement learning problem. Okay, so I'm going to save these to photos. Save. Let me make absolutely sure they arrived. Yep. Looks like they arrived. It's good. Okay. So I'm gonna, oops, my video is gone. Stop share. Share contents. Okay. So now we're gonna go back a little bit of theory. Oops. So back to some theory. And there are two parts of this. One, computing probability of, well, in this case, let's stick to the random dot kinematogram probability dots moving to the right. All right. And then two is choosing an optimal boundary. And for the dots moving to the right, I'm going to assume that here's our assumption. So at times t plus 1, t plus 2. I'm not really happy about this. So animal receives independent evidence about the moving dots. Okay, so and this is basically, so we get x1, x2, xt, right? And since we should really think of, 1 equals delta t. So this is some time scale later, maybe 100 milliseconds. What's really important is the evidence is independent, okay? And these are generated from P of, x t given c. So for instance, equals, for example, this might be Gaussian. So this is a really common assumption, e minus 1/2 x t minus c over sigma squared over the square root of 2 pi sigma squared. Which is basically what this says is, so xt equals c plus squiggle t, and this is 0 mean. So squiggle t is 0 mean, variance, sigma squared, okay? Or maybe it spikes. This is P of NL, number of rightward spurring spikes, number of leftward spurring spikes. Given C. Okay. And these are both from Poisson processes. And so we can actually work out later exactly what this probability is. But if the rightward neurons are firing at a much higher rate than leftward neurons, it's likely this is positive. Otherwise, it's likely it's negative. Actually, sorry, P of this is not the right thing. P of xt NL, well, yeah. So NL minus NR in time 1, which is really, remember, given C. We also take this time to be really small, so this is really either 0, 1, or -1. Okay, and this is now a Bernoulli process. Okay, so this is our setup. Okay, and now we can ask. So the question we want to know is P. What we really want to know is P of C greater than or equal to 0. Okay, given data. Now that's a little complicated, so we'll actually compute something easier. P of C, probability distribution over the coherence given data, equals P of data given C, P of C, this is our prior, divided by P of data. And this we don't, this is independent of C. So we don't care about. And our data, of course, is X1, X2, Xt. Okay. And P of data is actually kind of easy. So P of data given C is equal to product on tau equals 1 to T, P of Xt given C. Okay, so we can take logs again. Log P of C given data is equal to some constant, which is, this thing is minus log P of data. We don't care about it. Plus log P of C, that's our prior, plus the sum, tau equals 1 to T of log P of Xt given C. Okay, so this is our evidence. This is our evidence. Okay, and we now have a bit of a problem. And the problem is this depends on C. So it looks like, and remember what we have, once we have this thing, we can now integrate. So P of C greater than or equal to 0, given data, equals the integral from 0 to, well, in this case, 1, P of C given data times dc. Okay, so once we have this quantity, right, and we take care of the constant, we can do this integral, and we can do this. The problem, of course, is that we have to keep track of. Looks like we have to keep track of a whole function that depends on C, right? So evidence, we have to keep evidence for every different coherence, which is in general pretty hard. Okay, so what we do instead, so this is actually a general feature. We're going to come back to this when we look at the full reinforcement learning problem. But it turns out that some probability distributions make your life really easy. And technically, so we want, P of, so we need to keep track of P of Xt given C. Easy, or relatively easy, if P of Xt given C is in the exponential family. And this is actually if and only if. So I actually never in my life, never paid much attention to the exponential family. I know it exists. I rarely make use of this, but it turns out that almost every distribution you can think of is in the exponential family. Okay. And so in particular, Gaussian is in. So Gaussian, if P of X, actually we need to keep track of log. Gaussian P of xt given C is equal to e to the minus xt minus c squared over 2 sigma squared over the square root of 2 pi sigma squared. Okay. And log P of xt given C is minus xt minus c squared over 2 sigma squared minus 1/2 log 2 pi sigma squared. Okay. And this is equal to minus xt squared over 2 sigma squared plus cxt over sigma squared minus c squared over 2 sigma squared minus 1/2 log 2 pi sigma squared. Okay. So you'll notice, so if sigma squared does not depend on C, so we only need to keep track of xt and t, okay? And the reason for that is the sum on tau equals 1 to t of log P of xt given C is equal to C over sigma squared. The sum tau equals 1 to t of xt minus C squared over 2 sigma squared. The sum tau equals 1 to t of, well, 1. And then plus terms independent of C. Okay, so this term here is just t. Okay. And so if you keep track of, this is the evidence and this is time, you keep track of those two numbers, you know everything, right? You can read off the probability of xt given C, and then you can do an integral to get the probability of things on the right. So it's exponential family is really convenient. If sigma squared does depend on C, we have to keep track as well of this term. You have to keep track of this term as well, which kind of makes sense, right? You need this term to estimate the variance. But if your variance is fixed, you really just need this to estimate the mean, okay? And so a really nice way to do that is basically the plot on this axis. So the sum tau equals 1 to t of xt, okay? And then actually and so that's just cumulative, it's drift, and it's Gaussian, it moves around, and eventually you hit a bound. Okay. So this is choose right. Choose left. Okay. However, so in the case of the coin flip with 2 coins, it turns out the optimal thing to do is flat bounds. If you have a range of coherences, flat bounds is a bad idea. And the reason is, so if range of coherences, And the reason is kind of obvious. Let's say that on some trial, on this trial, this is a trial with coherence is really near zero. So you just kind of drift around like this. So this is C equals zero, okay? If coherence is zero, it's going to take a long time to reach the bound. So at some point you say, oh, I'm going to give up, right? The chance of me getting correct is really small. So what you really want the bound to do is to go down like this, okay? You want collapsing bounds. Okay. And the idea is there are some high coherence trials out there. If it's a low coherence, you might as well just give up. Okay. And that distribution of coherences is really important for how you make decisions. If you have very few zero coherence trials, your bounds will barely collapse at all. In a lot of zero coherence trials, your bounds will collapse much more rapidly. And this is a dating problem too. When do you break up with someone or marry them? Depends on the distribution of people in the world that you might date. Okay. So this is sort of a general picture you should keep in mind, but it's not really clear. If you'll notice, there were all sorts of complicated assumptions we made, and they were basically assumptions. This is kind of in some ways made up. Okay. And there's one more thing, and that is that the animals actually have a much harder job. So we can write this down because we knew exactly what the statistics were, right? But if you're an animal, you're not really sure. You have to learn all this stuff. Not only that, things can change over time. So I definitely want to consider the case where things can change over time and you can have multiple tasks. There are multiple things you can do in the world, right? If you're not studying for tests, you might maybe going to dinner or doing something fun, watching a movie. So in making decisions, you have to decide not only should I spend more time on this particular task, but if I switched, what kind of reward would I get? So we're going to actually do that. We're going to treat this as a reinforcement learning problem, actually solve it much more directly. And then we're going to go back to a little bit on experiments in this more complicated setup. So this is now sort of math. This is reinforcement learning. So this is a classic reinforcement learning problem. So as an animal, you get some evidence, you eventually make a decision, and you get a reward, right? You're right or you're wrong. And based on that reward, you have to modify your behavior. And reinforcement learning is formalized. So this is basically learning from the rewards. Rewards, okay. And reinforcement learning, it's a huge field. We're going to just scratch the surface. But it's sort of, the reinforcement learning researchers early on developed a nice mathematical framework for thinking about this problem, and divides the world into states, actions, and rewards. So basically, the world consists of states, actions, and rewards. So a state, we just write, this might be state 1, this is state 2, this is state 3, this is state 4. And as you go between these states, you collect rewards. This is R1 to 2. This is R2 to 3. R1 to 3. R3 to 4. And so your goal, and so you have some choice. If you're sitting here, you have some choice of which way you can go. Sometimes deterministic, sometimes probabilistic, but you always have some choice on what action to take. So you want to choose actions that maximize average future rewards. And it's basically average, the fact that you're trying to maximize average future rewards, it makes things hard. And that's why life is so hard, right? If we were greedy, life is really easy. So if we're not greedy, life is a lot harder. So suppose, for instance, that let's take an example. So this reward is this reward is big. We'll give it some numbers. So let's give it some names. This is 100, and this is 10, and this is 1,000. Okay. So if you're sitting here, you might think, oh, I'm going to get much more reward if I go that direction. Okay. But we have to look ahead, because this reward is actually minus 5,000 in whatever units, yuan, pounds, dollars, it doesn't matter. So if we actually don't go this way, which starts off looking good, all of a sudden we're stuck with minus 5,000. We collect our 1,000, and we end up with minus 3,900 or something. Whereas if we go this way, we do much, much better. And so reinforcement learning requires planning. And so how do we do that? We can only learn through rewards. Basically, all you can do is wander around, make decisions, get feedback, and modify things. And so so the mathematical formalism was to give each state has a value. Associated with state 1 is V1 equals value of state 1. State 1. And this is the important part, under a policy. Okay. So policy is basically it's action in each state. So we can lots of ways to write. We can write A of S like that. And so let's say your policy was to go from here to here to here to here. Okay. And so we'll give the end state, because that's the end state. We'll give this, doesn't really matter, you can pick anything, but we'll say for this one, so V4 equals 0. Okay. And so what this means is this state has, this state is easy. This state has value V3 equals 1,000. Okay, because you're going to collect reward of 100 when you go from here to here. Okay, so now this state, the value of state 1 depends on your action. Okay, if your action is to go this direction, then the value of this state is, in that case, the value of this state is, so let's say action A of S1 equals go to S2. In that case, V2, the value of state 2 is minus 4,000. All right, because if it's 4,000 here, so this is 1,000, you go from 4,000 from minus 4,000, and then you get a reward of minus 5,000, you end up with 1,000. Okay. We should sort of write down a kind of master equation. V in state N equals R going from n to m plus the value of state m. Okay, so the value is basically, it gets reduced by the amount of reward you get. So if you get 1,000, the value drops down. If you get minus 5,000, the value actually goes up. This state is worth a lot more than that one. You'd be much better off starting here than starting here. Okay, and V1 equals minus 4,100. Okay, because you get 100 here and going that way. On the other hand, if action in state 2 equals go to S3, and the value of 1 equals 1,100. Okay, it's worth a lot more. Okay, you lose 10 here, you lose 1,000 there, and so this is much more valuable, right? As you approach the reward, if you get positive in each step, as we approach the reward, these states are less valuable. Okay. So that's the basic setup, and this is sort of the important equation. Okay. This is the important equation which we're going to formalize. Okay. So what we're going to do next time is write down a formal way of solving this problem, of solving for values. So if you know value, you know everything under value under policy. So a formal way of choosing actions to maximize the value of a state. Okay. This one's kind of obvious. You might try this way and this way. You realize, oh, this is really bad, so we're just going to go this way. It's harder in real life because everything's probabilistic and and the world changes. It's hard to predict what's going to happen, but you can imagine doing this. Okay. So for next time, we're going to go in a little more depth into this reinforcement learning problem. We're going to apply it to decision making under time pressure, where there's a speed action trade-off, and then look a little more at some data. Okay, thanks very much. Normally I stick around, but since nobody asked questions, I'm going to leave in about a minute. But if anybody has any questions, I will be here for a little while.